Good morning, my lovely kiddos and my future mathematicians. Today we are talking about 7.4b, and we are going to be proving special parallelograms using points. So very similar to what we did in 7.3b, where we had to prove that parallelograms were actually parallelograms using either the distance formula on all four sides to make sure that the opposite sides were congruent, by using the slope formula to make sure that opposite sides were parallel, or by using the midpoint formula to make sure that our diagonals do in fact bisect. So today we're going to be proving special parallelograms are special parallelograms using something similar. Okay, so the first one that we have is a rectangle. Okay, and for this rectangle, remember that rectangles have our two rules in addition to our 5 super cool rules, but we also have that the diagonals are congruent and that all angles are 90 degrees. Okay, so they're all congruent, they're all 90 degrees. So that's what we're working with. Let me draw our points out here. So we have 4 points. We have point A at 2, 3. We have point B at 5, 9. We have point C at 11, 6. And we have point D at 8, 0. Our first thing that we have to do is we have to use the midpoint formula to prove that this is in fact a parallelogram, so that we can further prove that it is a special parallelogram. So we are going to look at the two diagonals, which are from, and I already sketched this out, but since we went over points on Monday, I'm just going to give you guys a rough sketch. We have B, C, D, and A. And so we are looking at the diagonals B to D and A to C. Okay, so let's do A to C first. Remember that our midpoint formula is M for midpoint is equal to x1 plus x2 divided by 2 and y1 plus y2 divided by 2. Okay, so for AC, I am using point A, which is at 2, 3, and point C, which is at 11, 6. So I'm going to pick point A to be my favorite. That's going to be my x1, y1, and point C to be my second favorite, or at my x2, y2. Okay, so we're just going to plug these numbers into our midpoint formula. So we have our x1, which is 2, plus our x2, which is 11, divided by 2, and then our y1 at 3 plus our y2 at 6 divided by 2. Okay, so 2 plus 11 gives us 13 divided by 2, which isn't going to divide clean, so I'm just going to leave it as a fraction. And then 6 plus 3 is 9 divided by 2, and again, that's not going to come out as a clean number, so I'm just going to leave it as a fraction. If you want to convert to decimals, that's fine. Okay, so we found the midpoint between A and C, so now we find the for the other diagonal between B and D. So point B is at 5, 9, and point D is at 8, 0. I'm going to pick B to be my x1, y1, my favorite point here, and D to be my x2, y2, or my second favorite point here. And we just plug it into the formula. So x1, which is 5, plus x2, which is 8, divided by 2, and y1, which is 9, plus y2, which is 0, also divided by 2. 5 plus 8 gives us 13, divided by 2, and since that's not going to come out cleanly, I'm just going to leave it as a fraction. 9 plus 0 gives us 9, also divided by 2. Again, that doesn't divide out clearly, so I am going to just leave it as a fraction. We can see that our two midpoints match, so this is in fact a parallelogram. Okay, so we proved that this shape is a parallelogram, but now we want to prove that it is a rectangle. So we're going to look at this first rule for rectangles, and that is that the diagonals are congruent. So we are going to use the distance formula to make sure that AC and BD have an equal distance. Okay, so that's our second step here. Okay, distance. Remember that our distance formula is d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, again doing AC first. Again picking A at 2, 3 to be my x1, y1, and C to be at 11, 6 to be my x2, y2. And remember that this does not matter. You can pick either point to be your favorite. I just picked these arbitrarily. And then we plug it into the formula. So we have the square root of x2, which is 11, minus x1, which is 2 squared, plus y2, which is 6, minus y1, which is 3 squared. Okay, so simplifying here, 11 minus 2 will give us a 9, and that is going to be squared in just a second here. And then 6 minus 3 gives us 3, which is going to be squared as well. 9 times 9, or 9 squared, gives us 81, and 3 times 3 gives us 9. We add these together, we have the square root of 90. Okay, so we're going to plug that into our calculator here. And we get a decimal. Remember, I'm only going out 3 decimal places for my approximation. 9.487. Okay? So now that we have the distance for AC, let's go ahead and find it for BD as well. So point B is still at 5, 9, and point D is still at 8, 0. I'm going to pick B to be my x1, y1 again, and D to be my x2, y2. Again, it does not matter. Okay, plugging this into the formula here, we have our x2, which is 8, minus our x1, which is 5 squared, plus our y2, which is 0, minus my y1, which is 9 squared. Okay, simplifying here, 8 minus 5 gives us 3 squared, and then 0 minus 9 gives us a negative 9 squared. 3 squared, or 3 times 3, gives us 9, and negative 9 times negative 9 gives us a positive 81. Okay, 9 plus 81 gives us the square root of 90, which again, if we plug that into our calculator here, we get our approximation of 9.487. Okay, so since the distances of our two diagonals match as well, so we know it's a parallelogram, and by doing the distance formula, now we know that this is in fact a rectangle. Okay, so our shape here is a rectangle. Okay, so our next special parallelogram is the rhombus. And remember, the rhombus has all 4 sides congruent, and that the diagonals are perpendicular. Okay, and that's in addition to the 5 super cool rules. These are just things that are exclusive to a rhombus. So again, we're going to have 2 steps to go ahead and prove that a shape is a rhombus. I'm going to write out our points here. So we have A at 1, 1, B at 5, 3, C at 3, 5, and D at 7, 7. So I'm going to give you guys a rough sketch because I did graph this already. Okay, so we have points A, B, C, and D. Again, the first thing we're going to do is we are going to use our midpoint formula again to make sure that the diagonals do in fact bisect each other, that they have the same midpoint. So our diagonals here are A to D and C to B. So let's find A to D first. Point A is at 1, 1, and point D is at 7, 7. I'm going to pick A to be my x1, y1, and D to be my x2, y2. And we're just going to plug that into the midpoint formula. Okay, so remember our midpoint formula is x1, which is 1, plus x2, which is 7, divided by 2. And then y1, which is 1, plus y2, which is 7, divided by 2. Okay, so these are identical here. 1 plus 7 gives us 8 divided by 2. 1 plus 7 gives us 8 divided by 2. When we simplify that, we get 4, 4. So the midpoint between A and D is 4, 4. Let's check it with our other diagonal, C to B. Okay, so C is at 0.35 and B is at 5, 3. Okay, so I'm going to pick C to be my x1, y1 and B to be my x2, y2. It does not matter. And we're going to plug these into our formula. So we have x1, which is 3, plus x2, which is 5, divided by 2. And over here we have our y1, which is 5, plus our y2, which is 3, also divided by 2. 3 plus 5 gives us 8 divided by 2, and 5 plus 3 also gives us 8 divided by 2. When we simplify that, we get 4, 4. Since the midpoints in both of our diagonals match up here, this is a parallelogram, so we can now specifically prove that it is a rhombus. Okay, so our diagonals bisect each other, so we definitely have a parallelogram. Now our second step, the step to prove that this shape is a rhombus, is to use our slope formula because we want to test that our diagonals are perpendicular. Remember, when perpendicular lines, they don't have the same slope, they have the opposite reciprocal slope. So one's positive, one's negative, and one looks like it's been flipped on its head. Okay, so our slope formula, since we haven't seen that today, is lowercase m is equal to y2 minus y1 divided by x2 minus x1. Okay, so we're going to find our slope of AD first. Again, A is at 1, 1, and D is at 7, 7. I'm going to pick A to be my x1, y1, and D to be my x2, y2. Okay, so we're just going to plug it into the formula. So we have y2, which is 7, minus y1, which is 1, divided by our x2, which is 7, minus our x1 of 1. So in both the numerator and denominator, 7 minus 1 gives us 6. 6 over 6, or anything divided by itself, remember, always gives you just 1. Okay, so let's now check the slope of CB here. So C is at 0.35 and B is at 0.53. So I'm going to pick C once again to be my x1, y1 and B to be my x2, y2. And we're plugging it in. So y2 at 3 minus y1 of 5 over x2, which is 5, minus x1, which is 2. So 3 minus 5 is going to give us a negative 2. And then 5 minus 3 is going to give us a positive 2. So ignoring the negative for 2 seconds here, 2 divided by 2 or anything divided by itself gives us a 1. But since these two signs did not match, we only had one negative. This is going to be a negative 1. Now, at first glance, this does not look like reciprocals. They're definitely opposites. One's positive, one's negative, but they don't look like reciprocals. But when we reveal the underlying 1 over 1, how we do with all whole numbers, we can see that if we took this fraction, flipped it upside down, and made it negative, we would get negative 1 over 1. So since our slopes are opposite reciprocal, it proves that our diagonals are perpendicular to each other. So this is, in fact, a rhombus. All right, and then our third and final special parallelogram that we have to prove using points would be our square. Okay, remember that squares, in addition to the 5 cool rules, they have all the properties of a rectangle, and they have all the properties of a rhombus. Okay, so this is actually going to have 3 tests as opposed to just 2 like the last ones. Okay, so our points are A at 0, -3, B at 3, 0, C at 0, 3, and D at -3, 0. Okay, a quick sketch here because I already did go ahead and graph this. So we have points D, C, B, and A. So our diagonals here are A to C and D to B. Okay, so remember the first thing we have to do is we have to test our midpoint to make sure that this shape is a parallelogram, because if it's not a parallelogram, then we just stop. Okay, so we're going to test A to C first. So point A is at 0, -3, which I'm going to make that my x1, y1. And then C is at 0, 3, which I'm going to make my x2, y2. Okay, and then we just plug it into the formula here. So we have, I'm going to try to squeeze it over here, our x1, which is 0, plus our x2, which is 0, divided by 2. And then our y1, which is -3, plus y2, which is a +3, divided by 2. 0 plus 0 is just going to give us 0 divided by 2. And -3 plus 3 is going to give us 0, also divided by 2. When we simplify this, we just have 0, 0. Okay, now we're going to go ahead and do the midpoint for BD. So point B is at 3, 0, which I'm going to make my x1, y1. And then D is at -3, 0, which I will make my x2, y2. Okay, plugging these in, our x1, which is 3, plus our x2, which is -3. Ooh, I didn't mean to put a parentheses, divided by 2. And then y1, which is 0, plus y2, which is 0, divided by 2. +3 plus a -3, that's going to go ahead and give us 0 divided by 2. And then 0 plus 0, again, gives us 0 divided by 2. When we simplify this, we have 0, 0. Since our midpoints match, then we know that this is a parallelogram, so we can continue on. Our second step, I'm going to break the rest of the page into 2 pieces here so we have enough room to do both of these. Our second step here is to go ahead and calculate the slope of the parallel lines to prove that they are perpendicular, just like a rhombus. Okay, so we're going to calculate the slope of AC first. A is still at 0, -3, which I'm going to pick to be my x1, y1. And then C is at 0, 3. That's going to be my x2, y2. Okay, so we're going to go ahead and plug that into our slope formula. So we have y2, which is 3, minus y1, which is a -3, divided by our x2, which is 0, minus our x1, which is also 0. Okay, whenever we have subtract a negative, we're really adding a positive. So 3 plus 3 gives us 6, divided by 0 minus 0 gives us 0. I don't know why I wrote 6 again. It's a 0. Remember, when 0 is on the bottom of our fraction at any point, this is an undefined line. Okay, so it has a slope of undefined. It is vertical. And then we are going to find the slope of B to D. B is still at 3, 0. It's going to be my x1, y1. And D is -3, 0 at x2, y2. Okay, so we're going to go ahead and plug that in. So we have y2, which is 0, minus y1, which is 0. And then we have x2, which is -3, minus x1, which is 3. So here 0 minus 0 is still 0, and 3 minus 3 gives us negative 6. 0 divided by anything is always equal to 0. As we can see, we have been flipped upside down. We cannot make this 0 negative. A negative 0 does not exist, but we can see that our fraction was negative. So these are opposite reciprocals, which means that our diagonals are perpendicular. So it would qualify for a rhombus at this point. But since we are trying to prove that it's a square, we have to do one final piece, okay? And that final piece, our third step, is to check the distance to make sure that the diagonals are equidistant, that they are congruent. Okay, so we're going to go ahead and check the distance between A and C first. A is still at 0, negative 3, which is going to be my x1, y1. And C is at 0, 3, which is going to be my x2, y2. Okay, so our distance formula, we have the square root of d for distance is equal to our square root of x2, which is 0, minus our x1, which is 0 squared, plus our y2, which is 3, minus our y1, which is a negative 3 squared. Okay, so 0 minus 0, that is just going to give us 0 squared. And then whenever we have a minus a negative, we're really adding a positive. So 3 plus 3 gives us 6 squared. Okay, 0 times 0 is still just 0. And 6 times 6, or 6 squared, gives us 36. When we add these together, we just get 36, which when we take the square root, we get exactly 6 units. Okay. Now we will test the distance between B and D. Point B is still at 3, 0. Whoa, I wrote that really small, which is going to be my x1, y1. And D is going to still be at negative 3, 0, which will be my x2, y2. Okay, so plugging that in, we have D for distance is equal to our x2, which is negative 3, minus our x1, which is 3 squared, plus y2, which is 0, minus our y1, which is also 0 squared. Sorry, that's a little cramped in the corner here. Okay, so negative 3 minus 3, that's going to give us a negative 6 squared. And 0 minus 0 is again going to give us a 0 squared. Negative 6 times negative 6 gives us a positive 36. And 0 times 0 is going to give us a 0 again. 36 plus 0 just gives us the square root of 36, which if we plug that in, we just get 6 units. So the diagonals are also equidistant, or they are congruent here. So since we've done all 3 steps, that we prove that it is a parallelogram by doing the midpoint, we prove that the diagonals are perpendicular by proving the slope is opposite reciprocal, and we prove that the diagonals are congruent with the distance formula, we can confidently say that this is a square.